F of z is given by this cubic, and we also know that minus 3 plus 4i is a root of f of z equals 0. Well, that means that minus 3 minus 4i is also a root, because it's the complex conjugate. And that is going to help us out, work out the full equation and hence find a and b. There's actually quite a few different ways to do this. I'm going to go through two or three. I mean, in the first one, it's kind of the same method. It's just there's a little different way to get the quadratic. I'm going to basically work out the quadratic that goes into this because I know what the roots are. And then I'll be able to figure out the other linear factor and I'll multiply them together and that will get me the cubic. So first of all, the longer way. So if like 4 was a factor, for example, then if 4 was a root, then z minus 4 would be a factor. Same idea here. Z minus 3 plus 4i is going to be a factor. And so is z minus 3 minus 4i. So I can work out this quadratic and then figure out, like I said, the linear factor. Okay, let's multiply it out. We get z squared minus 3 minus 4iz minus 3 plus 4i z, then plus minus 3 plus 4i times minus 3 minus 4i. Okay, actually, the i's will cancel because they're opposite signs and everything else is the same. We'll get z squared plus 3z, that's plus 6z. And then times in the complex conjugates, you actually just end up doing 9 plus 16 because the i's will cancel. And when you do 4i times minus 4i, you get minus 16i squared. So we get plus 25. Now let me show you how you can do that even quicker. And it's worth bearing in mind. It's like actually just going to save you time in the long run. Here's how we do it. Z equals minus 3 plus or minus 4i. I'm going to write it like that. It's like I've just solved it by completing the square and you get a plus or minus because guess what? We're going to write it back in completed square form. So then z plus 3 will equal plus or minus 4i, and I'm now going to square. So z plus 3 squared is equal to minus 16 in both cases. Expand this, z squared plus 6z plus 9 plus 16, that's plus 25, is equal to 0. So I've just basically shown that that is the roots. If the roots are minus 3 plus or minus 4i, then they solve this equation here. And hence that equation there will go into this one here. So let's figure out what we're left with. So if we have z squared plus 6z plus 25, what do I need to times by to get that? Well, I'm going to need a z because that will guarantee me the z cubed. And if I do 175 divided by 25, I get 7. Okay, it has to be a 7 there. In fact, it has to be a plus 7. And that will now help me find out a and b because all I've got to do is expand it. So I will get z cubed plus 7z squared plus 6z squared plus 42z plus 25z plus 25 times 7 is 175. Oh yeah, we knew that one. That gives z cubed plus 13z squared plus 67z plus 175. So therefore, A, that's the z squared term, is going to equal 13, and B is going to equal 67. So that's method one, but I found the quadratic factors in two different ways. I'm going to very quickly overview a second method. I'm not going to go through the whole thing. I actually did go through the whole thing. I just realized this, no, I don't need to learn to do it this way, so I don't want to spend a lot of time on it. But you could just sub in one of the roots into the original quadratic and create an equation involving a and b. And I'm going to show you what happens very quickly. I've actually called it method 3 here because I'm going to show you method 2 in a minute. But yeah, you find out z squared, z cubed, you sub it all in, and you end up getting a real and imaginary part. And you can set the real part equal to 0 because that's the right hand side, and the imaginary part equal to 0. You create two simultaneous equations, and then you can get a and b from there. Oh, that is just so. unnecessarily complicated. Good to be aware of it, so I'm glad I just brought it on the screen, but I'm not going to go through the whole thing. Method 2 then is to use the equations from roots of polynomials. The sum of the roots is going to equal minus capital B over capital A. I've used them because actually it's not this B here. I'm just going to write out the general form A z cubed plus B z squared plus C z plus D equals 0. That's our general cubic. And then the sum of the pairs is equal to capital C over A, pairs, and then the three roots multiplied together is minus D over A. So we can use some of the ideas that we've got. We would have to, first of all, you would probably, this would equal minus D over A, it would equal minus 175, because D is equal to 175 here. So then the 3 multiplied together is minus 175. You could times the 2 together, which gives us, we've already worked it out before, that gave 25. And that would mean that the other root was minus 7. So gamma is minus 7. Remember, we already showed earlier that z plus 7 was a root. So I'm going through this quite quickly, but I'm basically saying this is alpha and this one's beta. And then we can work out the sum of the roots. So it's just going to be, I'm struggling for space here, but the minus b over a is then going to be minus 3 plus 4i, minus 3 minus 4i, and then minus 7. So these cancel. We're going to get minus 6 minus 7, that's minus 13. And we can see that a is 1, so b is just going to be 13. But that b is this b here, confusingly. So actually it's a equals 13. And I've found it out. And then finally we could do the product of the roots. Oh, I'm not going to go through that, but we would times, no, let's do it. So it would be alpha beta plus beta gamma plus gamma alpha is equal to C over A, which in this case is just B. Now we've already worked out alpha beta, that's the 25. That's when you times the two complex roots. And then it would be plus minus 7 times minus 3 minus 4i. Actually, sorry, it was a plus 4i for the first one. Then minus 7 minus 3 minus 4i. And that, remember, is equal to, we just said B. So the i's cancel. It's going to be 25 plus 21 plus another 21 gives us B, and it ends up being 67. So 3 methods, just to clarify. We found the quadratic factor. I think this is the best way to go. Showed you how to do it in 2 different ways, then worked out what the missing bracket was, expanded it, we're there. Method 3, which I didn't go into detail on, was to just substitute a root in, get an equation in terms of a and b, look at the imaginary and real parts. Method 2 is just to use roots of polynomials from the very beginning, and use the minus 175 to work out the missing root, and from that you can do the sum of the roots and sum of the pairs to work out the missing quantities. Okay, just go with one of them. I would say method 1 is the best. Part B asks to show all the roots on a single Argand diagram. So we've got these as our roots. Let me just put them down here. Real axis, imaginary axis, minus 3 plus 4i. Put minus 3 here. And this is approximately 4. That's going to be my 4i. And I'll put just a little cross there. And then minus 4i. Here's minus 4. Put a little cross there. So those are my 2 complex roots on the Argand diagram. I like to connect it up to the origin. You don't have to. I think it enhances it. And then minus 7, I'm going to go along the negative real axis to say here. And I'll just write the roots by it. So we've got minus 3 plus 4i, minus 3 minus 4i, and of course minus 7. Finally, for 1 mark, write down the roots of the equation f of z plus 2 equals 0. So this is just a translation by minus 2 in the, well, z in the x direction, really. So all that's going to happen is every root, I need to subtract 2 from it. Therefore, I will get minus 5 plus 4i, then minus 5 minus 4i, and finally minus 7 minus 2, minus 9.